This is purely, let's say, an analytical problem from the field of calculus, and we must, before we go ahead, we must first define what is orthogonal trajectories. To explain, I have taken two sets of curves, family of curves actually. This one is a set of curves which we will designate as C1, let's say. And this one is another set of, another family of curves which we will designate as C2. Now, we say that C1 and C2 form a set of orthogonal trajectory pairs when each member of the set C1, we've just drawn three, there will be many others, is intersected by any member of C2 at right angles. In other words, these angles are all 90 degrees. This looks very close to 90. The others don't look so fine, but the principle can be understood. So I repeat once again, the concept of orthogonal trajectory is, it is essential to consider two families of curves designated by, let us say, C1 and C2, and the criterion is that any member from C1 intersects any member from C2 perpendicularly, that is, orthogonally. So let us take an example to understand, and let's also try and see how we can get to the orthogonal trajectory. So the problem breaks down to, given C1, how does one get to C2? In other words, this contains many members, this contains many members, infinite actually. Now let us suppose that we start with C1 and write its equation as f x y and dy dx is 0, where the equation has xy terms and slope terms. Now this dy dx is the slope of members of C1. If we have one member of C1 intersecting another member of C2 perpendicularly, if here the slope is dy dx, then evidently the slope for this curve is -1 by dy dx for C2, because lines that intersect each other, they have slopes which are related by m1, m2 is equal to -1. So if this is the set of equations, or the differential equation that gives C1, then to get the members of C2, all we need to do is, instead of dy dx, we write -1 by dy dx for this. That will give the orthogonal trajectories for C1, f x y -1 by dy dx as 0. In other words, all we have to do to get to the orthogonal trajectory is to take the original curve equation and replace each dy dx term by the reciprocal of itself with a sign changed. We'll take an example to understand this further. I have chosen a very simple example. So we will see, find the orthogonal trajectories to the family of curves represented by x squared plus y squared is equal to C. This is a single parameter family of curves. Actually, it is just a family of circles whose center is the origin and whose radius is the under root of C. C is equal to R square actually. Now, to get the orthogonal trajectory, what we do is we differentiate these once. Let's see. So we get 2x plus 2y dy dx is equal to 0. Now this is the slope, relating to the x and y coordinates of the circle. So we write dy dx is equal to minus x over y. By what we have just stated, the slope of any member of the orthogonal family will be plus of y over x. That means take a reciprocal and change the sign. So if our circle is the family of curves initially, then for any member of the orthogonal trajectories, we will have its dy dx, take a reciprocal and invert the sign, change the sign. So y over x. This tells us dx over x is dy over y. dy over y is dx over x, and this implies log ey is log ex plus c. If we write this c as log e a, then what we get is this will imply that log y is log ax. In other words, y is equal to ax. Now this is a straight line, a family of straight lines passing through the origin, and that's expected because if we have a circle with center at the origin, and if we draw a straight line through the origin, obviously the two curves will intersect at right angle. This is the one is tangent, the other is the normal. So that's as expected. We can take other examples. Well, that's all for now.